Yes.
Sorry, can you hear me?
Yeah, I hear you.
Yeah. Okay, because I can hear you very low. Sorry.
So,
Okay.
your voice is very good.
Better now?
Your voice is fantastic. Very nice.
Okay. Thank you. Should I share my screen?
Yeah, please.
Can you see my screen?
Yeah, great.
Okay, thank you for the invitation to present our work. I know that it's very late right now there, so we really appreciate all your efforts for attending this presentation. Please feel free to ask any questions and I will try my best to reply them. So I've been working at the Research Institute of Textile Chemistry and Textile Physics of the University of Innsbruck since 2013. And I've been working with conductive textiles, especially on the topic of energy storage. And I will show you in this presentation also some part of my work. But first, I would like to make a general introduction and an overview of the topic. Sorry, wait a second. So first, I would like to introduce. So I would like to talk about the materials used in conductive textiles, the processing techniques to prepare these conductive textiles, and then I will talk about some applications, especially in the topic of wearables, sensors, and energy storage. And finally, I will describe some challenges and also opportunities in this topic. So there are two ways of using this, the materials for creating the conductive textiles. And one is the direct use of conductive fibers or metal wires. I apologize because here we cannot see the picture. Could you see the picture? No. But, yes, sorry for the inconvenience caused.
Okay, no problem.
We try to do the presentation in the room from the institute.
Where is the
Okay, sorry for the inconvenience caused. I hope you can see the slide. Materials, can you see them?
Yes.
Okay. Unfortunately, this picture, you cannot see them, but well, I was just saying that we can use directly conductive fibers or metal wires to form these conductive structures. And in this picture, you could have seen some carbon fibers. But no worries, later on there will be more pictures. And another method to create these conductive textiles is to produce some conductive coatings on the non-conductive textiles. And here on the right side, you can see a kappa-coated fabric. Yeah.
This is
Okay.
fine.
Yes. This is the kappa coating on non-conductive textiles, in this case, polyamide. So we can find three different type of materials, metals. We can find zero yarns, metal wires, kappa wires. We can also find yarns that are, for example, polyamide, that they are coated with a metallic coating. Or we can also find wires that have a combination of different metals, for example, nickel or copper. And another material that is used is carbon. We can find carbon particles coated on a fabric. We can find the direct use of carbon fibers to create these conductive structures. We can also find some nanostructures, for example, carbon nanotubes, graphene, graphene nanowalls. The third material is conductive polymers. There we can find two groups: the intrinsically conductive, that this is polymers that are conductive by itself. These polymers, they have a special chemical structure where you have the combination of single and double bonds. This is the conjugated double bonds structure. You can have this conductivity on the polymers. And another strategy is to use conductive fillers like carbon fibers in a non-conductive polymer. And then this conductive polymer is called extrinsically conductive. We can classify these materials by three main properties. Just put here the conductivity, the mechanical properties, and the chemical stability. So each of these materials, they have their own advantages and disadvantages. For example, now we start with the metals. The metals are very highly conductive, and they also have high thermal conductivity. The mechanical properties are also, they have also very interesting mechanical properties, not like they are ductile, they can drawn into filaments. They are tough, they are malleable. The problem is that they are very rigid, and then this could bring problems to the comfort of the textiles. They have also very high weight. And the highest disadvantage is their poor chemical stability. They can be corroded, no? They have a very poor corrosion resistance. Carbon-based materials, they are very interesting because they have high conductivity, not so high as the metals, but pretty high. Carbon fibers, they have a very nice mechanical properties. They have a very high strength and high stiffness, and they also have a very high fatigue resistance. They're also lightweight. They are not perfect because they can easily break when they are bended. So this creates some problems when we create these conductive textiles with carbon fibers. Another advantage is that they are very stable electrochemically. They do not corrode, and also they are very stable at different environmental conditions, different pH. So this is the positive and the advantages. The problem, as we said, is the poor flexural strength, and this makes very difficult for the textile processing of these materials. Conductive polymers, they are not so, the conductivity is not so good. There are strategies to increase the conductivity. One strategy is to dope the polymer. When they are doped, the conductivity is increased. They are transparent and lightweight. This is very interesting. And the chemical stability is also very interesting. They are electrochemically stable, and they are also biocompatible. This also opens new uses, for these conductive polymers. They are also flexible. but in general, their mechanical properties are poor. They are very brittle, and they have very poor strength, and it's also difficult to use in the textile processing. So now I will talk about the different techniques used to create the conductive polymers. We are saying that we can use directly conductive fibers or wires, metallic wires. Here you can see some examples of different wires and yarns. In the first pictures, you can see a yarn where there is a twisted metal wire around the yarn. In the second picture, you can see an example of a metal coated yarn. And in the third picture, you can see another example of a yarn that contains multifilaments. We can use these different structures, yarns, to create different structures using weaving, knitting, embroidery, tufting, among others. Now I will explain the different techniques. Weaving. For the weaving, we have two yarns, the warp. This is the horizontal yarn and the weft. This is the, this the warp is the vertical and weft is the horizontal. Here in these pictures, you can see some examples now where you can use this, the kappa twisted yarn, for example, not to create a conductive structure. And we can see here this conductive filament. Or this is another example where they have created this mesh also inside this woven structure. And in the case of the carbon filaments, I told you that it's very difficult to process them, but for the weaving, it's possible because the bending curvatures are not so high. So inside the textile, so it's possible to create these woven structures with the carbon filaments. The woven structures are usually very dense and not very flexible. So another technique that it's very interesting to create stretchable conductive structures is knitting. So knitting is, I just put here now two examples of how the threads are combined to form these knitted structures. We can have weft knitting, where we can see this, like these loops here in this direction. And then we can have also the warp knitting where the loops are not in a single direction. So here you can see, can you hear me?
Yeah, it's very good.
So here you can see also some pictures with different knitted structures. In this case, they use this P.PS. This is the conductive polymer. And here we can see the different types of knitting that they use. And in the first picture, for example, we see that they use this. This is a plain knitted structure where all the structure is conductive, where they use this polymer, this filament, conductive filament. And here we can see different combinations of non-conductive and conductive filaments. The different combinations for sure will give different responses of the textiles that we will talk later about this. Another processing technique is embroidery. This gives you the advantage that you have more freedom in the design. For the embroidery, we have like two different types of embroidery. One is where we have like an upper yarn and a lower yarn that they are combined, forming a different, this is like a embroidered structure. Here we can see an example. This will be the that you have a supporting fabric, sorry, you have a substrate, and then you combine this upper and lower yarn to form the shape that you wish. And here you would see this, no? They have a non-conductive substrate fabric, and then they use these silver-coated yarns to form these antenna shapes. The other embroidery technique is called tailored fiber placement. There you would have a substrate, and you would place, we have a yarn guide, and you will place the yarn in the direction that you wish. And here we can see an example. This is a picture from our institute, where we have an embroidery machine, and we can create these structures where we have a woven carbon fabric as a substrate, and then we can place the carbon filaments in the directions that we wish. So this, what I have been explaining, these are the general techniques used to insert or to use directly use conductive yarns and fibers. And now I will explain about the techniques used to create conductive coatings. So here you see an overview of the main techniques. I will start. So the electrochemical deposition could also be called electroplating. In this technique, what we have is 3 electrodes placed inside a solution. And what we do is in one of these electrodes will be the substrate that we want to coat it. And what we do is to apply a certain current or voltage, and then some redox reactions will occur, and there will be the solution will contain the ions of the source material that we want to deposit, and then there will be some coating deposited on the substrate depending on the current and the conditions that we apply. Here, the advantages is that we have good control of the morphology and the thickness, depending on this current and the time that we use for the deposition. And it's a simple process, and we have a high deposition rate. The disadvantage is that we can only use this technique when our substrate is already conductive. So here we cannot deposit conductive coatings on non-conductive substrates. So this technique, it will be used, for example, to coat wires, that we have these wires with different, for example, copper wires coated with silver or with tin. We will use, for example, this type of technique, but we would not be able to use non-conductive textiles. So these other 2 techniques, physical vapor deposition and chemical vapor deposition. So they both have a source of material where we evaporate or decompose, and then it will be deposited again on the substrate. So in the physical vapor deposition, the target, the source of material, is a solid. And in the chemical vapor deposition, the source of the material is a liquid or a gas. And in both techniques, we need a vacuum. And the process, it allows you to create very thin layers. So the deposition is in the atomic level. Here it allows you to create high purity thick coatings. And also you are able to control the structure, the stoichiometry of your coating. And it also provides you a high adhesion, but it also depends on the substrate. If you have a 3-dimensional substrate, we have some shadows. No, you have to imagine that the position, no, that you apply some energetic beam, no, to your target, and then all the atoms from your target will be directly deposited on your substrate. And this makes that if your substrate has a three-dimensional structure, there will be shadows. There will be parts that will not be covered by the material. The disadvantages we have mentioned already, that you need a vacuum, and also that there is a lot of material that will be lost. There will be a lot of material, the reactor will be coated by the source of the material and not only the substrate. So another two are the thermal spray coating and plasma spray coating. So in these two techniques, what you do is to evaporate, to melt your source of the material. In the case of the spray coating, no, you have this spray gun where the source of the material is continuously provided. And then you will heat it. Now you will apply some current that will heat your material, and it will spray it and coat your substrate. In the case of the plasma spray coating, you will have in your plasma gun, you will have an anode and cathode. You will create some current that it will create this plasma, and this plasma will melt your source of material that it will be finally deposited on your substrate. The advantages is that you can create very thick coatings, and also in desired locations where the spray is located. But you have to be very careful when your substrates are heat sensitive, because there will be damage. And the other two, screen printing and inkjet printing, these are very interesting techniques for coating. So here how it works is that you have a screen with a pattern, and then you use a conductive ink, and then you spread and transfer your coating entirely to the fabric, to your substrate, with the pattern that you wish. In the inkjet printing, this transfer is done through the nozzle, through the inkjet nozzle that is spread the ink with your conductive material directly on your substrate. Here you can use many materials. You can use conductive polymers, carbon, copper, silver inks. The problem will be that you need always to cure in order to have these conductive lines. You will transfer your conductive ink into your fabric, and then in form of particles, and then to form the conductivity. These conductive lines you will need to cure and to condense these particles, not to unify these particles to form these conductive lines. And this for this you need temperature, and this will also be a problem depending on your substrate. You have also the problem of the resolution of your pattern. The resolution is limited to some micrometers. And the last technique is electroless plating, or also called electroless deposition. Caroline will talk later about this technique, but I just want to mention that we have been using this in our institute for creating conductive textiles. And the advantage is that you can use rough substrates like textiles, so that you can get high conductivity in your conductive coatings, and that you have a uniform thickness. And one of the disadvantages is that it may require the use of expensive catalysts like silver or platinum. But Caroline will talk later with more details about this technique. So I hope you had now an overview of the different techniques used. And now we will continue with the applications. So one of the main applications of conductive textiles is for stretching sensors. There are different principles that to get this stretching sensor. One is through the resistance. So the idea is that we have these conductive textiles, these coating yarns, they have their own resistance. And the idea behind is that when we stretch the textiles, this resistance will change and we will have our sensor. This is the most investigated system. And the advantage is that the response, they are very stable for large strains. You can really apply a large strain and you will have a different resistance. And the problem is that they are temperature and humidity sensitive, dependent. The resistance will change depending on the temperature and also depending on humidity. This could also be an advantage because you could also create a different type of sensors, temperature sensor. We will talk also later about this. And another problem is the response of the resistance versus the stretch, the strain. That is non-linear and it has some hysteresis. And the other principle is capacitive stretching sensors. So the capacitance to measure the difference capacitance when we apply a force, a strain. So here how it works is that we have two electrodes. So two conductive textiles, two conductive structures. In the middle, there is a dielectric, a non-conductive material. And the thing is, when we apply some voltage, there will be some charges separated between these two electrodes. These charges will create a capacitance, and this capacitance will change depending on the distance of these electrodes. The positive thing is that this dependence is linear, so we have a linear response of this sensor. It's temperature independent. It has also a low pressure detection limit, and disadvantages is that it has low sensitivity, and it's also the distribution of these charges is susceptible to environmental interferences. The third principle is the piezoelectric. Here we have again two electrodes, two conductive structures, and in the middle we have a piezoelectric material. A piezoelectric material is a material that creates a voltage difference when we apply some force. And this is very interesting because this sensor is self-power. It has a very high sensitivity to dynamic pressure. It has also very fast response, but the problem is that the response can drift over time. Then it has lower reliability. And when there is a static force, when there is no force with a static movement, there is no response, no voltage difference. And the last one is the sensors based on the triboelectric effect. Here what we have again is two conductive substrates, and in the middle we have two non-conductive materials, different materials with different polarity. And the idea is when we put in contact these two materials, there will be a distribution of charges. And when we separate these materials, this distribution of charges could create some current to reach the equilibration. And this is what we will measure. So it has also the ability to be self-powered. It has high sensitivity, a fast response, but it's also, the durability is also low, and this current is also very limited. So now I will give you some examples of the most investigated system, the resistive stretching sensors. So here you can see some knitted fabrics. So as I explained before, knitting is the processing technique mostly used to get stretchable fabrics. So it is normal that they use the most common technique to create stretching sensors. Resistive stretching sensors will be with the knitting. And here you can see an example now of different knitted structures with a silver-coated yarn. For the evaluation of the performance, it's important to measure the sensitivity. How is this change in the resistance versus the strength applied? The sensing range, so how much strain can I apply? The stability, the long-term stability, and then also the response. How fast is the response? Here I show you the resistance differences versus the stretch. And here we can see that the authors now of these investigations, they show different responses for the different knitted fabrics. And what they have observed is that the resistance decrease when we apply some stretching. And this is because what they explain here, now that we increase the contact points between the different yarns, and this makes that the resistance is lower when we apply some strain. So they use this to create some sensors to measure the breathing rate. And here you can say, no, they select the best sensor that they have, the best structure, and you can see here the different, how they monitor this breathing rate from the participant. So this will be one example of application. Another one is, so here we can see also a similar knitted structure where they use the silver-coated yarn to create these conductive structures. And the idea is to monitor the human motion with the change in the resistance. And here they present some results, how this resistance is changing depending on the different movement of the participant. So these are examples now how to use the resistive stretching sensors to monitor human motion. Another application is as a temperature sensor. I have already mentioned that the resistance can change with temperature. And this is called a thermistor, and they can use thermistors not to measure the temperature. But now I would like to talk about thermocouples. So some work that we have been done here in our institute. So thermocouples is based in, we have two metals. When we have two metals that they are both subjected at different temperatures and they are in contact, there will be some difference voltage that you are able to measure. And this is called the Seebeck effect. And here I show you some experiments that we performed. First, we had a lyocell fabric. And what we did is the electrolysis kappa deposition to get the conductivity, conductive textile, a copper-coated textile. And what we did is to create this temperature sensor, combining this copper-coated textile with aluminum stripes. We have two different metals, copper and aluminum. The copper was at higher temperature, heated area, and aluminum was at a lower temperature. This is called the cold areas. And then we were able to measure the different voltages. And here I show you, the sensitivity of the sensor independently of the temperature. Here we can see when the copper coated fabric was at 40 degrees and when it was at 60 degrees, and the aluminum stripes were at room temperature, about 20-25 degrees. And we have observed that the sensitivity was constant, was remaining during the time. After 2 months and after 4 months, we were still able to use these temperature sensors. Another application is for electrocardiograms. So this is to measure the electrical impulse from the heart. And the conventional electrodes that they use are silver chloride electrodes, a gel with adhesives. And the problem is with these adhesives is that they create discomfort in the patient and they leave marks. And also the conductive gel dries over the time, and this impacts the signal. Some researchers are trying to develop conductive textiles to be used for the same purpose. And here I show you some examples where they use this silver-coated nylon yarn to create this knitted structure. And here you can see the conventional electrodes, the different response with the heart rhythm. And here will be these conductive textiles. So although the resolution is not the same, there is still a lot of work to do, but they are able to measure the signal, and there's already some advance on this direction. Another application is for electrochemical energy storage systems, and this is where I've been working. So, and the idea in lithium-ion batteries, our idea was to substitute the conventional current collectors that they used for conductive and broader structures, textile structures. So the idea, the conventional battery, how it works is that we have 2 electrodes separated by an insulator. And in these 2 electrodes, we have a copper foil coated with an anode material. And in this other electrode, we have aluminum foil with a cathode material. And this cathode material is the one that contains the lithium ions. And when we charge the battery, the lithium ions from the cathode material are inserted into the anode material. And when we discharge the battery, the inverse process occurs. So the thing is, we had the idea to use these 3-dimensional structures obtained with embroidery. Instead of aluminum foils, of copper foils or aluminum foils, we had the idea to increase the surface area to be able to insert much more of this electroactive material, to increase the energy density of the batteries. And then what we did is to create these embroidered structures. And then we tried different formulations not to increase the mass loadings on these electrodes. For sure, we have to design. So this was to design thick batteries. So usually all these layers, you have to imagine that they are very thin because of the addition of the electroactive material. And in our case, our idea was to use thicker electrodes to increase the energy of the batteries. But we had to design new electrode formulations. And this is what we investigated also now. We tried to investigate different electrode formulations, mixing this electroactive material that contains the lithium ions with different compositions. So between the binder and the thickener, And our idea was to study the different performance of the batteries, how the capacity is changing, how much current can I apply. And what we observed is that there was an optimization between this, the composition between the binding and the thickener. So here you can see the different behaviors of the when we charge and discharge the battery, the capacity, how much energy can these batteries have. And then here we were doing some experiments increasing the current, and also during time, how stable were the batteries. So another application in the topic of batteries that we are also investigating is the use of embroidered carbon structures as electrodes. In this case, we have a different type of battery. This battery is, we have 2 tanks, so 2 electrolyte solutions, 2 solutions where we have different electroactive species dissolved in these solutions. So these redox species, they are at different oxidation states. And the thing is that the species, these electrolyte solutions, they circulate through the electrodes. And then they need to be, so we charge the battery, so some reactions will occur inside these electrodes. The current will be transferred from the electrode to the solutions, and then there will be some oxidation and reduction of the of our electrolytes. And this there will be stored in the tanks, and afterwards, when we want to discharge the battery, the solutions will circulate again through the electrodes, and the inverse reactions will occur. Spontaneous reactions will occur, and the current, we will get the current from these electrolyte solutions. So the idea here is conventional electrodes, they use non-woven structures, that this is randomly distributed carbon fibers. And our approach was to use this embroidery technique to orient the fibers in certain directions to improve this circulation of the electrolyte during the redox reaction, during this electron transfer from the electrode to the solutions and from the solutions to the electrode. So what we observed is that the use of these structures allow to have lower pressure drops within the cell. And this helps you to improve the efficiency of the battery. And also we observed that the electrode surface utilization was higher. And that means that we could transfer more electrons in a more uniform distribution than in the conventional structures. Also, the higher, we observe that the mass transfer coefficients was higher. That means the distribution of the concentration of these species inside the electrons was more uniform due to this distribution of these fibers. So now I have analyzed the applications, and now there will be only 2 more slides about challenges and opportunities. Okay, challenges. We see that it's difficult, so we need to create ideal conductive yarns and fabrics because we wish to maintain these electrical properties during the fabrication process. There will be some mechanical stress, and the electrical conductivity needs to be remain the same, and also after the daily use. especially for the aging. They will be aging. So this is some challenges of these conductive structures. So there will be some environmentally conditions. No? For example, if we wish that the conductive fabrics need to be washed, and then they need to sustain their electrical properties after all these processes. The complexity of the products, this is also another challenge. We have seen that this is like a multi-step process where we first, for example, we want to coat the yarn, and then we use the yarn in the textile manufacturing. So this is a complex process that the manufacturers and need to understand. And also, when we have the final product, conductive textile, the end user needs to understand how to use this. It needs to be user-friendly. So there are also difficulties to how to connect this this conductive textile with electrical components that are non-textile. For example, with conventional batteries or conventional data transceivers, that they are not designed for conductive textiles, for textiles. So there is this difficulty. And most of the devices are in this development phase. So they don't reach to the market, and maybe because of the lack of large scale production, too high cost for mass production. So these are things that we need to consider when a conductive textile is developed. And there are also lack of standards, testing and certification. And this is because it's very difficult to classify the conductive textile. Is it a textile? Is it an electronic component? It's difficult, its classification. But there are also opportunities. So we have seen that the textiles offer some advantages over other materials, and we have seen that they offer high surface area, that they are lightweight, that they are soft, deformable, so that they can cover large surface areas, that we can add local functionalities. Another opportunity is that there are so a lot of working on this topic. So researchers and technology developers are continuing advancing on this field. There are more and more solutions to problems. Another opportunity is that there are already miniaturized and also flexible microelectronic components available. So they are also developing electronic components with these characteristics that can be attached to a textile. And this offers also opportunity in professional markets, for example, in personal protection and defense, professional care, professional sports, functional interiors. So markets where you need this constant monitoring of health and the performance conditions. And we have seen that it's possible not to offer solutions that are cost saving and also with this value enhancing textile-based solutions. The solutions provided by textiles, they can offer, so the textiles can offer to this market solutions that are not yet available. So thank you for your attention. And I would also like to thank the funding agencies, FFG and the COMET program. Thank you.